What is CHF580? It is a technique that combines femtosecond laser ablation with spark-induced breakdown spectroscopy and a calibration-free approach to enable quantitative elemental analysis of materials without the need for standard reference samples. In other words, the calibration-free method is a quantitative analysis technique that does not rely on standard. The aim is to address the limitations of traditional methods in the elemental analysis of magnesium alloy.
Calibration-free femtosecond laser ablation spark-induced breakdown spectroscopy is highly valuable for the elemental analysis of magnesium alloys due to its ability to deliver accurate results without the need for external calibration standards. This technique relies on the analyzed emission line to determine key plasma parameters such as temperature and electron density, which are then used to calculate elemental concentration. The use of femtosecond laser pulse ensures precise ablation with minimal thermal damage, while the spark-induced breakdown enhances sensitivity, enabling the detection of trace, minor and major element with improved accuracy. By avoiding matrix match standards and compensating for self-absorption and matrix effect, CHF580 offer a fast, reliable and highly sensitive method for quantitative analysis in magnesium alloy application. Here, direct spectral comparison between FSLA-SIBS and femtosecond LIBS in two spectral range between 300 to 400 nm in figure A and 400 to 500 nm in figure B. On both graphs, the orange line is FSLA-SIBS and it clearly has much greater peak intensities than FSLIBS. We can observe, for example, strong emission line for elements like aluminium, copper, zinc and especially magnesium, with very strong magnesium peak at 447.78 nm. This intensity increase is due to the breakdown caused by the spark after the femtosecond laser ablation, which is increasing plasma excitation and emission efficiency. The FSLA-SIBS method also produces better defined peaks and a higher signal-to-noise ratio, making it more suitable for trace and minor element analysis in magnesium alloys. Overall, this figure confirms that FSLA-SIBS significantly improved analytical performance, providing a more sensitive and robust technique for elemental analysis without needing calibration standards.
Next, moving on to qualitative analysis. Let's look at how we identify the elements present in magnesium alloys using this method. The key principle here is the plasma emission spectrum. When the femtosecond laser ablates the surface of the magnesium alloy, it generates a high energy spark that forms a plasma. This plasma contains excited atoms and ions, which then emit light as they return to lower energy states. Each element emits light at specific wavelengths, creating unique emission lines, almost like a fingerprint for each element. Next, this light is then collected and analyzed using a high-resolution spectrometer. By performing spectral matching, we compare the detected wavelengths to non-standard, which allows us to accurately determine which elements are present in the sample. This process is highly sensitive and precise, making it a powerful tool for elemental analysis in complex material like magnesium alloys. Next is quantitative analysis. It determines how much each element is present. This is where the calibration-free method comes into play. With this approach, we don't need pre-made calibration standard. Instead, we calculate the plasma parameters, specifically the plasma temperature and electron density based on the intensity of the emission lines. To do this, we use a Saha-Boltzmann plot, which helps us estimate both the temperature and the excited state population of the atoms in the plasma. We also apply partition functions and perform equation fitting to refine our result. Additionally, the electron density is determined from Stark broadening. This refers to the widening of spectral lines due to electric fields in the plasma. To ensure the accuracy of our calculations, we validate the plasma mix local thermodynamic equilibrium (LTE) condition. This is essential for the CF method to be valid. Finally, after all these steps, we are able to compute the exact concentration of each element present in the alloy with high precision without the need for external calibration standard.
According to the data gathered in this study, we can see a number of important outcomes that confirm the effectiveness of the FSLA-SIBS technique. Firstly, the FSLA-SIBS method offers 3 to 15 times the intensity of emission compared to common FSLIBSE. Increased intensity makes it more sensitive to the identification, not only the main elements present in the alloy but also the secondary and trace elements, which are normally difficult to measure accurately. Although a calibration-free method FSLA-SIBS achieves very accurate results, concentration of element is it quantified had less than 10% relative error against certified reference value. This shows that the method is capable of yielding accurate quantitative results without external calibration. The method was capable of analyzing several important elements in magnesium alloy like magnesium, aluminium, zinc, copper, iron, manganese, silicon and nickel. This shows it's a very useful tool for multi-elemental analysis in one pass, especially for alloy characterization. The generated plasma was very hot at around 10,000 Kelvin and highly electron dense These plasma conditions are ideal for local thermodynamic equilibrium or LTE, which is required for accurate calibration-free analysis from emission line. Another important strength is the low metric effect. The emission line in the spectrum were clear and crisp with minimal background noise. It indicates that although magnesium alloy may have complicated composition, the measurement is stable and accurate. Finally, this technique is practical and time effective. It doesn't need any chemical digestion or calibration standard, and it can analyze the sonic sample directly. This makes it particularly suitable for fast on-site elemental analysis in research or industrial setting. So overall, the evidence clearly shows that FSLASIBS is not only sensitive and accurate, but also effective and adaptable, putting it squarely in the frame for modern elemental analysis, especially for metallic alloy.
You must be wondering why we choose this method. Now, let's look at the key advantages of using the calibration-free FSLIBS technique. First, it is calibration-free, meaning we don't need any standard reference materials. This simplifies the process and reduces preparation time. It is also allows for rapid and in-situ analysis. That means we can perform fast, real-time detection directly at the sample site without needing to transport it to a lab. This is ideal for field work or industrial settings. Another major strength is its multi-element capability. With just a single measurement, we can detect and quantify multiple elements at once, saving both time and effort. Next, the technique also offers high sensitivity with significantly lower detection limits compared to traditional FSLIBS methods. This makes it suitable even for trace level analysis. Since it uses femtosecond laser pulses, the method is non-destructive and requires minimal sample preparation while also reducing thermal damage to the sample surface. Lastly, it is cost-effective in the long run. By eliminating the need for reagents, standard calibrations, and frequent maintenance, it helps cut down on operational costs and minimize waste. While the calibration-free FSLIBS method offers many advantages, it's also important to acknowledge its limitation. First, the technique involves complex data analysis. It requires intensive computational work, including iterative calculations and advanced algorithms, which can be challenging and time-consuming. Secondly, the matrix effect is not fully eliminated. When dealing with complex or unknown sample compositions, it can introduce uncertainties that affect the accuracy of quantitative results. Next, we have instrument sensitivity and cost. The high-end equipment required for FSLIBS can be expensive and demands careful calibration and regular maintenance, which adds to operational complexity. Another limitation is its precision in ultra-trace detection. Compared to more sensitive techniques like ICP-MS, FSLIBS may not perform as well when detecting elements at extremely low concentrations. Lastly, there's the risk of equipment overload, especially when operating at high discharge voltage. This could lead to system failure or damage if not properly managed. Despite this limitation, many of them can be addressed with proper setup, software support, and experience handling.
Even FSLASIBS is already a very powerful and accurate method, there are several basic improvements that would take its performance to the next level. First, we need to reduce variation between each laser shot. This slight variation can affect precision, especially in quantitative analysis. By averaging a number of shots or using a moving stage where a fresh surface is presented for each shot, we can stabilize and render the readings more reproducible. Second, the timing of the delay between the laser ablation and the spark discharge is critical. The plasma will not be optimum excitation if the timing is not optimized. Fine-tuning this delay can be used to enhance signal strength and overall detection of major and trace elements. Another challenge is self-absorption, where excessive plasma density leads to emission lines being reabsorbed and giving incorrect results. This may be minimized by utilizing emission lines that are less susceptible, or by implementing correction models to mathematically adjust the intensity. Finally, while the current setup is okay in the lab, it's not portable. Making a handheld miniaturized version would allow for in-the-field real-time alloy analysis. For example, in factories, repair shops, or even mines, that would make FSLASIBS much more convenient and commercially relevant. By placing these four elements, consistency, timing, accuracy, and portability, first we can make FSLASIBS not just more accurate but also more flexible and useful in a wide range of applications.
This slide summarizes the key performance metrics of the calibration-free FSLIBS method used in our study. Starting with accuracy, the method demonstrated reliable results with relative errors within 30% for most elements and impressively less than 5% for aluminium and zinc. Next, the precision of the system was excellent thanks to high signal stability, which ensures consistent results across multiple measurements. In terms of sensitivity, the method showed steep calibration curve slopes, particularly for Elements like aluminium, zinc, and copper, which indicate strong responsiveness to concentration changes. Looking at the detection limits, we achieve good result, where aluminium at 28.93 ppm, zinc at 22.73 ppm, manganese at 10.86 ppm, silicon at 2.79 ppm, copper at just 2.13 ppm. The method also showed strong selectivity with minimal spectral overlap and reduced matrix effects, owing to the high-resolution spectrometer and the calibration-free approach. Finally, in terms of robustness, the technique maintains stable performance under various experimental conditions, showing its reliability for different applications. Altogether, this result highlight the method's strength in both qualitative and quantitative elemental analysis.
So it's end of our presentation. Hope you guys get an idea from our slide and presentation. Thank you.